A frozen lake surface in early June possesses a specific kinetic tolerance. It can take, for a moment, the sliding scrape of a roughly 3 to 4 ton fighter spreading its weight across a broad belly. But once that forward energy bleeds off, the problem stops being momentum and becomes bearing capacity. Late-season freshwater ice can be honeycombed with warm cracks and rot. Under a sustained load, it creeps, sags, and fractures in bending. The margin between holding and failing can collapse in minutes. The objective in this case was to locate and extract an intact 1942 airframe from a remote subarctic lakebed for historical preservation. The target was a Hawker Hurricane Mark IIB bearing the serial number Z5252. It had rested undisturbed for more than 6 decades and submerged in a remote subarctic lake west of Murmansk in the Kola region. Delivered to the Soviet Union with RAF 150 First Wing, the fighter was passed into Soviet units defending Murmansk and the approaches to the Kola Inlet. This was a machine built of mixed materials. Its primary structure was a steel tube fuselage with heavy alloy mounts up front. Aft, wooden formers and stringers shaped the body, and fabric skin carried the finish. That hybrid build dictated its vulnerability not just in the air but under the water. On June 2, 1942, the pilot executed a forced wheels-up landing onto the frozen surface of Lake Nyalyaver. The aircraft slid to a halt, structurally intact. The immediate consequence of the landing was survival, but the physical environment imposed a strict time limit on the hardware. Early summer in the subarctic creates severe thermal instability in freshwater ice. While the surface remained solid enough to handle the initial impact and deceleration, the stationary mass of the heavy metal forward section concentrated downward pressure on a localized area. Thermal degradation of late-season ice drastically alters its structural integrity. Moving, the ice could take the scrape; stopped, it could not take the weight. The margin vanished. Before Soviet salvage teams could arrive with rigging to spread the load, the weakened ice gave way under the aircraft. The fighter slipped through and sank to the bottom. It was written off as an uneconomical recovery, left to settle in the silt. For more than 6 decades, the hurricane remained trapped in an isolated geographical footprint. Far enough west of Murmansk to keep casual discovery unlikely, the lake became a natural vault. The physical parameters of this vault created a highly specific set of environmental conditions that would dictate the eventual terms of its recovery. The initial survival of the airframe upon ditching established a baseline for future search teams. Because it did not shatter on impact, its structural geometry remained contiguous. A contiguous airframe presents a vastly different salvage profile than a scattered debris field. However, there were no precise coordinates to return to later, only a rough description preserved in wartime reporting and archive paperwork. The frozen surface of Lake Nyalyaver spans a wide area, rendering visual surface markers completely absent once the ice melted. Every subsequent winter cycle locked the lake down under a new sheet of ice, while summer thaws obscured the depths under turbid water. The recovery operation would not launch until over 6 decades later, driven by archival research rather than immediate military necessity. The gap between the loss and the extraction meant that any recovery team would be dealing with deeply altered materials. The heavy engine block would inevitably sink deeper into the lakebed, while the lightweight timber frame of the tail would be subjected to complex biological and chemical pressures. The original decision to abandon the aircraft in 1942 was entirely rational based on the tactical realities and limited salvage equipment available on a melting tundra lake. Attempting to extract a waterlogged fighter plane through broken ice without heavy lifting gear would have risked further equipment loss for a depreciated asset. Therefore, the airframe was left to its environment. The primary unknown remained what specific mechanical failure forced the aircraft onto the ice in the first place. A fighter pilot manages airspeed, altitude, and mechanical integrity as an interrelated energy system. When combat damage removes one of those pillars, the remaining 2 must be spent precisely to reach the ground intact. During that close-quarters engagement, Lieutenant P.P. Markov was piloting the aircraft against German Messerschmitt Bf-109 fighters, described in some accounts as the E model. The hurricane absorbed heavy punishment. The port wing was holed. The upper engine cowling was pierced. Accounts also describe damage to the fuel system and the cockpit instruments. The airframe held together, but the machine was no longer fit to fight. Any one of those hits could force an immediate and irreversible pivot. With damage accumulating and the risk of fire or mechanical failure rising by the second, Markov broke contact. He traded altitude for distance and searched for the only runway the tundra could offer, a frozen lake. The decision logic was absolute. He had to trade his remaining kinetic energy for distance and a survivable landing site. Markov abandoned the dogfight and converted his altitude into a controlled mechanical glide. He kept the landing gear retracted to prevent a violent flip upon contact with the uneven surface, like executing a disciplined belly landing that distributed the impact forces across the lower longerons. This maneuver successfully managed the thermal degradation hazard of the late spring ice, allowing the pilot to walk away. However, once the ice failed and the aircraft slipped beneath the surface, gravity and fluid dynamics took control of the airframe. A World War II fighter with a massive V-12 engine possesses an extreme forward center of gravity. As the Hurricane descended through about 18 meters of water, roughly 59 feet, the heavy steel and alloy engine block rotated the aircraft into a steep, nose-down pitch of around 60 degrees. The forward section impacted the lakebed with significant force, burying the propeller spinner and engine cowlings deep into the sediment. The rear fuselage, constructed entirely of lightweight timber, formers, and fabric canvas, was left extending upward. In a typical freshwater tundra lake, the environment aggressively metabolizes organic material. During brief summer thaws, biological decay rates accelerate. Wood and canvas submerged in these conditions generally rot within a few seasons, leaving only the bare metal framework behind. The critical variable in Lake Nyayavur was the exact composition of the lakebed at the impact coordinates. The aircraft did not strike bare rock or sand. Instead, that steep nose-down angle drove the forward fuselage into a roughly 1.5-meter-thick mat of aquatic moss and silt. This dense organic layer likely altered the microenvironment around the wreck. A thick botanical mat can limit water movement and reduce how much fresh oxygen reaches buried material. That kind of shielding can slow decay, especially for fabric and wood that would otherwise be exposed. If the tail remained wrapped and protected in that sediment, it helps explain why so much survived. The preservation, then, was less a miracle than an accident of crash geometry and local conditions. Finding a structurally intact airframe on a lakebed is rare, but the challenge then shifted to how future survey teams could successfully pinpoint a wooden and canvas tail hidden beneath dense Arctic moss and deep water. A freshwater tundra lake conceals its bottom topography beneath layers of turbid water and accumulated sediment. Visual observation from the surface is entirely ineffective for recovery operations. To locate a submerged 60-year-old airframe, a search team must rely on instruments that can penetrate the water column and differentiate artificial geometry from natural geology. After archive research resurfaced key wartime paperwork in 2001, Russian survey teams began mapping candidate lakes in 2003, working from the rough sectors described in those records. The immediate constraint was the sheer size of the potential search area. Sweeping a vast lakebed requires balancing the speed of the survey against the resolution of the data. The team needed a sensor capable of covering wide areas rapidly to establish a localized search box. The initial pass utilized a magnetometer. A World War II fighter contains massive iron and steel components, concentrated in the engine block and the forward armor plating. These dense ferrous elements distort the local magnetic field in their immediate vicinity. By towing the sensor across the lake in a carefully plotted geometric grid, the survey team measured these invisible distortions. Maintaining precise parallel track lines is essential to ensure no gaps exist in the coverage area. The magnetometer successfully detected a strong ferrous anomaly, indicating a heavy metallic mass resting on the bottom. However, a magnetic distortion only proves the presence of metal. It cannot determine if the object is a contiguous aircraft, a scattered debris field, or discarded industrial equipment. To resolve the target, the search progressed to the next phase of the operational sequence. The team returned in February 2004 to conduct a high-resolution sweep. In midwinter, as they deployed side-scan sonar to build a physical profile of the anomaly, Acoustic target verification relies on transmitting sound waves through the water and measuring the return echoes. The sonar pings reflect differently depending on the density and shape of the objects they strike. This acoustic profiling differentiates the hard, unnatural straight lines and right angles of an aircraft structure from the soft, irregular mounds of natural lakebed anomalies. The resulting acoustic shadow confirmed an intact aircraft profile resting in 59 feet of water. The geometry of the sonar return perfectly matched the dimensions of a Hurricane fighter. Yet, acoustic data alone does not satisfy the strict requirements of historical evidence. Verification required physical proof of identity to definitively link the wreck to the specific 1942 combat event. The final phase of the search involved sending a diver down through an access hole cut into the frozen surface. The diver descended through the 59 feet of dark water to conduct a tactile and visual inspection of the site. Operating in a confined overhead environment beneath the ice, the diver faced severe visibility limits. This constraint required approaching the fragile tail section with extreme caution to avoid accidentally damaging the historical artifact or stirring up silt that would blind the camera. The orientation of the wreck provided a crucial advantage for identification. Because the heavy forward engine section had buried itself into the silt, and the rear fuselage and tail assembly remained elevated, in that oxygen-starved pocket, the fragile timber and canvas had endured. The fabric covering the horizontal stabilizers was completely intact. The diver illuminated the underside of the tailplane with a localized light source and recorded the surface using an underwater video camera. The footage provided the primary anchor proof for the entire expedition. Clearly visible on the preserved canvas, stenciled in standard Royal Air Force typography, was the original serial number. The video confirmed the designation Z5252. This chain of evidence, from archive paperwork to a magnetic anomaly, to an acoustic shadow to visual confirmation, left little doubt about what lay on that lakebed. The team had found its artifact. Verification was complete. But the subsequent challenge shifted to how an Overland salvage team could extract such a fragile airframe before the tundra lake froze solid again. A recovery operation operating at the edge of the winter freeze faces a strict meteorological deadline. Plunging temperatures and deteriorating surface states dictate a hard operational boundary, compressing the available time for underwater rigging and heavy lifting. By October 2004, the environment at Lake Nyaljaver was rapidly collapsing. Surface temperatures hovered between 37 and 39 degrees Fahrenheit. High winds drove heavy snow flurries across the choppy water, creating severe hazards for diver safety and surface vessel stability. The window for extraction was closing, requiring an immediate logistical push from the recovery team. The specialized dive group from Voronezh, led by Boris Osetinsky, understood that the physical extraction required heavy industrial equipment not locally available on the remote tundra. Their method involved transporting massive metal lift pontoons and diving hardware 1,200 miles overland via truck to reach the lake shoreline. Once at the edge of the water, the team had to establish a staging area in the freezing mud. They began moving the heavy pontoons out over the exact coordinates identified by the earlier acoustic target verification. The primary engineering challenge waited on the bottom. The aircraft was buried nose-deep in a dense bed of silt and moss, and the lakebed's suction locked the forward fuselage in place. And simply running a winch line to the tail and hauling would have guaranteed catastrophic failure. The rear structure was wood and fabric, and any concentrated lift while the nose stayed glued in mud would snap the spine of the aircraft, destroying the artifact's integrity. To extract the Hurricane, the divers turned to a pontoon displacement lift. The concept is simple and brutal. Strap buoyant metal volumes to the strongest nodes, then feed them air until the lake becomes your crane. But the reality was not clean. Even with care, the first lift fractured the weakened rear structure, and the tail section broke away. After that failure, the rigging plan had to be adapted so the remaining airframe could be raised without tearing itself apart. Operating in near-freezing water with limited visibility, the divers routed lifting straps around the forward metal structures and kept every load path off the preserved canvas and timber. Because the center of gravity was heavily biased toward the V12 engine, the rigging had to be balanced to prevent the tail from swinging wildly the instant the suction broke. Once the rigging was secure and inspected, the surface team began the slow process of pumping compressed air down to the metal pontoons. The operation required extreme patience to avoid a sudden, uncontrolled ascent. As buoyancy increased, upward tension slowly equalized with the holding force of the suction until the mud finally released. The airframe broke free from the lakebed. Supported entirely by the metal lift pontoons, the massive structure began a slow, controlled climb through the dark water. The divers monitored the rigging geometry as the combined mass of the aircraft and the lifting gear moved toward the surface. The buoyancy had to be constantly managed to ensure the aircraft maintained a stable attitude during the vertical transit, preventing the lift lines from cutting into the surviving aluminum skin. When the metal upper cowlings finally breached the choppy surface of the lake, the immediate extraction phase was successful. However, the hostile surface conditions presented a new hazard. The wind and driving snow continued to batter the exposed structure and the rigid metal pontoons. The artifact was now subject to the kinetic energy of the surface waves. The recovery team had to immediately secure the floating assembly to a tow line. The airframe had successfully broken the surface, but the critical question remained whether the transitional stresses of an overland tow would compromise the perfectly preserved wooden tail section before it reached the shoreline. Getting a damaged airframe from neutral buoyancy to shore is where things can come apart. Once it breaks the surface, it loses the even support that water provided, and the load shifts hard onto temporary rigging and pontoons. The priority becomes control. Keep the assembly stable, keep the tow steady, and avoid any dynamic shock that would flex weak joints or let metal hardware strike the skin. They had to beat the freeze, reaching the extraction point before the lake surface locked up again. The Voronezh dive team successfully completed the slow surface tow, bringing the aircraft into the shallow mud of the shoreline. This marked the completion of the wet recovery phase, but the physical reality of a 1,200-mile return transport dictated an immediate dismantling sequence. Reports also indicated the aircraft came up with ordnance still present, a hazard that demanded strict explosive safety handling by qualified personnel. A World War II fighter cannot be loaded onto a standard commercial trailer fully assembled, especially not when the intended route involves unpaved subarctic roads. The sheer physical dimensions of the wingspan and the overall length of the fuselage exceed standard logistical transport limits. Furthermore, the structural joints of the airframe had been absorbing water for 6 decades. Attempting to hoist the aircraft as a single unit using a shoreline crane would focus immense shear stress on the weakened wing roots and corroded engine mounts. To survive the overland journey, the aircraft had to be methodically separated into its primary modular components right there on the frozen riverbank. The engineering team established a secure load-bearing datum on the frozen mud to support the fuselage. They initiated a controlled disassembly specifically targeting the original factory structural brakes designed into the Hawker airframe. The first priority was to reduce size and snag points for transport. The team removed large external assemblies and panels, including the wings and cowlings, until the wreck could be moved without the structure tearing itself apart. With the aircraft broken down to what the route could tolerate, it was prepared for overland haul out from the lake. Once the massive structural components were separated, the team faced the delicate challenge of stabilizing the fragile timber and canvas rear fuselage. This specific section was heavily saturated with lake water. If it was permitted to dry too rapidly in the frigid open air, the sudden evaporation would cause the ancient wood fibers to shrink, twist, and warp, which would permanently destroy the original aerodynamic geometry. The fabric covering was equally vulnerable to sudden contraction and tearing once it lost its internal moisture content. To mitigate this handling risk, the team constructed specialized wooden transport cradles designed to perfectly support the unique physical profile of each separated component. These custom cradles distributed the inevitable kinetic shocks and vibrations of the overland journey evenly across the strongest internal bulkheads. The individual parts were carefully secured, padded, and wrapped in protective layers to actively manage the evaporation rate during the long transit out of the tundra. The physical recovery from the immediate hazard zone was complete, and the artifact had survived both the lakebed extraction and the complex shoreline dismantling process. The investigative teams had successfully pulled the machine out of its remote natural cache, But the institutional custodians now faced a critical decision regarding how to preserve an artifact defined entirely by its combat trauma. The arrival of a recovered airframe at a conservation facility triggers a definitive institutional choice, and the engineering team must decide whether to return the machine to a pristine factory state or to freeze the physical evidence of its operational life. For the Hawker Hurricane at the Zadorozhny Museum of Technology, the curatorial mandate was strict. Full restoration fundamentally destroys the archaeological record. It requires replacing the original 1942 material with modern fabrications, stripping away the oxidized surfaces and repairing the structural failures. That process would permanently erase the kinetic impact signatures on the cowling and the torn fabric of the tailplane. Therefore, the institution rejected a mechanical rebuild. Instead, the objective became stabilization, treating combat damage and lakebed residue as the artifact's value, not defects to be erased. The immediate constraint was the move from saturation to air. Once exposed, oxygen and shifting humidity would restart the decay that had been paused for 62 years. Before any drying, conservators rinsed away trapped sediment and contaminants, then slowed and controlled moisture loss, so wood, fabric, and corroded metal would not tear, twist, or warp. The work was meant to be careful, documented, and reversible wherever possible. The preservation that saved the rear fuselage came with its own handling penalties. As damp fabric and paint began to dry, layers could lift and flake. On the surviving surfaces, markings associated with Soviet service could still be seen over earlier finishes, and every surviving scar was photographed and logged before any stabilization. Where pigments or fibers threatened to shed, for conservators used minimal consolidation to keep what remained from turning to dust. Mounting the aircraft for permanent public exhibition introduced a severe mechanical trade-off. The load-bearing strength of the original wooden formers and the internal metal spars was permanently compromised by decades of water absorption and galvanic corrosion. The aircraft absolutely could not support its own weight if placed on its original landing gear, nor could it be suspended from the ceiling using its factory lifting points. The engineers had to design a custom internal armature to solve this structural deficit. A hidden steel framework was fabricated to carry the massive static load of the V-12 engine block in the forward fuselage section. This modern support structure was carefully threaded through the existing inspection panels and access hatches. The strict rule of the conservation team was that no new holes could be drilled into the 1942 metal to accommodate the modern mounts. The armature bypasses the fragile historical joints, transferring the immense weight of the aircraft directly to the museum floor. The completed exhibit places the Hurricane in a wide diorama, recreating the feel of its forced landing on the frozen tundra. The fighter sits, wheels up, pitched forward, framed as a recovery and survival story rather than a showroom rebuild. What stands here is a scarred airframe, left in the condition that combat and water recorded, an exhibit of restraint, not reinvention. It reads as a decades-long forensic record shaped by impact, immersion, and the hard compromises of salvage. The legacy of the operation is not perfection, but restraint, preserving what could be proven and stabilizing what could be saved. The machine remains a permanent, measurable artifact of the forces that brought it down and the engineering constraints required to bring it back.